Two of the most well-supported advancements in physics appear to disagree. The first is Einstein's theory of general relativity. It excels at describing large-scale phenomena and has been groundbreaking in understanding how gravity works, but it relies on a smooth, continuous universe and for particles to have a definite nature. Quantum mechanics, on the other hand, can accurately predict the small-scale behavior of matter and energy. It relies on matter and energy being in states of probability, contradicting the certainty outlined by general relativity. Think of quantum mechanics as describing a constantly fluctuating universe. Subatomic particles are traditionally thought of as rigid points, but if a particle were to exist in this uncertain environment, it would be violently affected, making it difficult for general relativity, which depends on certainty and a smooth, non-fluctuating spacetime, to coexist with quantum mechanics. This is where string theory comes in. Imagine instead that a subatomic particle was actually a filament of energy, or a string, and that the frequency at which the string vibrates would determine what type of subatomic particle it is. So if everything in our universe is made up of these strings, studying them could in turn reveal a larger truth about the universe. The particle was more violently affected by the jitters. A string has more flexibility, and it would not be as affected by this uncertainty. Its general position remains relatively unaffected. By modeling subatomic particles as strings, the uncertainty of quantum mechanics could be mitigated just enough to allow general relativity to exist within the same system. There is just one problem. For string theory to be possible, at least 10 dimensions, including the 4 that we can observe naturally, would need to exist. Sounds impossible, but think about it this way. From far away, a rug might appear 2-dimensional, but look closer and you'll see it has height. It's a 3-dimensional object. Look even further and you'll see the complex loops and texture on its surface. It was more complex than originally thought. The texture and complexity of the rug is similar to the concept of additional compacted dimensions. We sometimes visualize space with a grid. Let's imagine a grid with the smallest unit of measurement possible. These extra dimensions may be found here. They would have to be complex shapes in order to accommodate the minimum 6 additional dimensions required. This is where Calabi-Yau manifolds come in. Basically, they're geometrical spaces where individual regions look like flat Euclidean space. You could disassemble the manifold's pieces and reassemble them into a flat plane. But there's a problem. When solving for a Calabi-Yau manifold that would supply 6 additional dimensions, there are tens of thousands of solutions, with there being no current way to identify which manifold is the correct one. And another issue, string theory is virtually untestable. The strings would be too small to be observable to scientific equipment. It's thought that colliding particles with the particle accelerator may result in gravitons being ejected to the unobservable dimensions. We could support this by finding that the final energy measurement is less than the initial energy measurement. But we would need a particle accelerator the size of the solar system to confirm this. So, has everyone abandoned string theory? No, there are thousands of physicists still studying string theory and its potential, even if it's been pursued for nearly a century. And the buzz around string theory has sparked mathematical research, for example, findings related to Calabi-Yau manifold. Even though physicists are still searching for its end, unraveling string theory has been a thread of discovery in its own.